Hello everyone, I am Tushar Prakash and today I will present our work Pyramidal Spectrum Frequency Based Hierarchical Vector Quantized VAE for videos, which also known as PVQ-VAE. In modern video generation model, they mainly rely on VAE to compress high-dimensional videos into compact latent representation. Especially discrete VAs are quite powerful in this regards because they convert token videos into tokens. And second, transformers can model these tokens quite efficiently, which in turn enable scalable video generation. However, existing discrete video VAs have two key limitations. First, they operate purely in the spatial domain, and second, they quantize feature at only a single resolution. From a signal processing perspective, this is suboptimal because video or image is inherently multi-scale and frequency structured. So our key question is, can we design a VAE that respect the frequency and hierarchical nature of video signals? Now, first of all, let's talk about why frequency modeling matters. If you can see here in the bottom left, the feature captured using convolution and FFT has a very distinct profile. The FFT and DWT, which are like frequency domain analysis, can capture a very refined and sharp feature as compared to convolution maps. Now, this is because like convolutions are local operators. Even deep CNN approximate global contexts indirectly. But video and other visual data contains first global layout and motion, which is low frequency structure, and second, fine texture and edges, which are high frequency structure. Also, multi-scale spatial and temporal information are there in the case of videos. The frequency domain naturally separate these components. So instead of relying on convolution, we explicitly model frequency information. Now, if you see in the middle, we have provided the architecture of proposed the PVQ-VAE. So in the encoder part, uh, it has two complementary branches. First one is FFT branch, which actually responsible for the global structure, we can say. It transform feature into frequency domain, capture long range spatial correlation, and model global scene layout and structure. This improves structural consistency, long range coherence, and motion stability. Now there is a DWT branch, which is actually responsible for multi-resolution details. Now, wavelet decompose features into chorus structure, directional edges, and fine details. Wavelet preserve spatial localization while enabling multi-resolution analysis. So, FFT intends capture global structure. DWT, discrete wavelet transform, is responsible for localized multi-scale details. They both are complementary. Now, regarding the quantization, traditional uh, VQVAs quantize only the final encoder output, but video and other visual uh, information is hierarchical in nature that we discussed earlier. They have chorus motion patterns in the case of videos and intermediate object structure, also fine texture. So we introduce pyramidal vector quantization PVQ. Instead of quantizing burns, we quantize at multiple encoder stages. Conceptually, chorus level encode global structure, and finer level progressively refined details. This improve rate distortion trade-off, byte allocation across the scales, and expressiveness of discrete tokens. Now, there was a paper called very recent paper, Magbit V2, which argues that using a large vocabulary for quantization can help in capturing fine details as well. But traditional vector quantized VAE requires large embedding tables, which is memory heavy and can unstable the training. So we use lookup free quantization LFQ, where tokens are compact binary codes and vocabulary is scale efficiently, which in turns make the training quite stable. This enables large discrete vocabularies without exploding memory. Now, uh, videos tokens are highly correlated across space and time. So we use a transformer prior to model token deficiency. Second, improve entropy efficiency. Also, enhance temporal consistency. Additionally, we use a pre-trained high fidelity VAE, which actually transfer high frequency perpetual priors, improve sharpness, and enhance visual realism. Now, why this all works? So our improvement came from three principles. First, explicit frequency modeling. Second, multi-resolution hierarchical quantization. And third, structured token dependency modeling. Together, they improve compression efficiency as well as reconstruction fidelity. Now, if we talk about the results, you can see here we have achieved SOTA performance on CocoWell and WebWidWell. Now, also at the strong compression of bitrate 0.034 on MGCL JCB dataset, we have also achieved the SOTA performance. Qualitatively, you can like clearly see as compared to other baselines, PVQ-VAE can reconstruct sharper edges, better motion stability, and improve texture uh, preservation. Ablation study confirm if we remove the FFT, then global structure degrades, and if we remove DWT, uh, textures degrade. Also, multi-stage PVQ consistently improve performance. Now, all in all, PVQ-VAE shows that video quantization should explicitly model frequency structure as well as multi-skill hierarchy. Now, by combining spectral modeling, wavelet decomposition, hierarchical quantization, and efficient discrete vocabulary, we can achieve state-of-the-art reconstruction under strong compression. Thank you.